All right, this video is about tonicity, which is the relative concentration of solutes dissolved in a liquid, like how much sugar is dissolved in water, how much salt is dissolved in water, or even how many proteins, any type of molecule. So I have here two different situations to compare, one where there's a lot more solute in the cell and one where there's a lot more solute in the surroundings outside of the cell. I wanted to show you that I can use the word hypertonic and the word hypotonic to describe this one situation. So, for example, the cell is hypertonic to its surrounding. Hyper meaning more, tonic meaning solute. But I can also say about this same picture that the surroundings are hypotonic to the cell, hypo meaning low solute. So I can use those two words to describe the same picture. It's all about making sure you're careful about what you're comparing to what. So this has more solute than the surroundings. The cell is hypertonic, whereas the solution is hypotonic. Now in this picture, the cell is hypotonic compared to the solution, and the solution is hypertonic compared to the cell. As a reminder, water moves toward the solute. So in this picture, water is going to be going into the cell towards that solute. In this picture, the water is going to be exiting the cell. It's going to be going towards the higher concentration of solute. So this cell might swell and burst, where this cell is going to shrivel and get smaller. As a reminder, isotonic means the same concentration. So if the surroundings and the cell had the same concentration of solute, we would say that they are isotonic to each other. So one way that we talk about tonicity is by talking about the water potential of a solution or of a cell. So as a reminder, the formula for water potential is water potential equals pressure potential plus solute potential. You don't need to remember this because it's on the formula sheet right up here, which you're going to have access to for the AP exam. So in terms of this picture, where there's more solute inside of the cell is hypertonic to the outside of the cell. In this case, we see that the water is moving from outside to inside, so that can help us identify that there's higher water potential outside of the cell and lower water potential inside the cell, because water moves from high water potential to low water potential. So like I said, the surroundings, oops, I forgot the G, surrounding water potential is greater than the cell's water potential in this example, because water goes from high water potential to low water potential. Another term you might hear used is osmotic pressure. More osmotic pressure means more likelihood for the water to move. So in this picture, the outside has more or a higher osmotic pressure as compared to the inside, because water is moving out of that and into the cell. Now, remember, dynamic equilibrium is something to keep in mind. I keep saying water's moving into the cell. Water's moving out of the cell too, but it's such a small amount compared to how much is moving into the cell. So water molecules are going both ways, but there's a net flow inside of the cell in this case. Now, there's another equation too on the formula sheet that has to do with water potential. It helps you solve for solute potential. And it's negative ICRT. You don't have to have memorized in your head what any of those letters mean. It's all on the formula sheet. Hold it a little closer so you can see. I is ionization constant. It's 1 for sucrose. It's 2 for NaCl for salt. You're going to have to remember that one, that it's 2 for salt, because salt ionizes into Na and Cl. C is molar concentration. R is a constant and it gives it to you, and T is temperature in Kelvin. So if they give you Celsius, you add 273. So I'm going to do an example problem with that in a moment. But first, I want to remind you of an experiment that we did that had to do with water potential and tonicity and the movement of water. And that is when we put potato cores into those different colored solutions that had different concentrations of sucrose in them. And you didn't know ahead of time what the concentration of each one was, but you were able to figure it out based on seeing how the potato cores either grew or shrank. So here's an example of one student's data output from this experiment. She made a graph where she graphed the percent change of the potato core mass, like how much did it increase or decrease, versus the concentration of the solution. So we were able to figure out the concentration of the solutions by thinking about how they change. So the one that was most concentrated with the most sucrose made that potato core shrink the most. So this student was able to figure out that that was this one, the red one, that was the most concentrated. The one that was pure water made the potato core swell up because the water was going into the potato core where there were more solutes than there was in plain water. And so this student figured out that that was this one because the mass increased. And then we graphed this data and we were able to find the concentration of solute in the potato core. So it happened to be that we had a data point, let's see, or I guess not in this case, but so we were looking for where our line of best fit crossed the x-axis. So in this case, it was at about 0.3 molar. So our potato core probably had about a 0.3 molar concentration. That's where it would have been isotonic to the solution if we had a 0.3 molar solution to put it in, meaning the same amount of water going in as coming out. And as a reminder, you were then able to pick a follow-up where you brought in from home some sort of fruit or vegetable, or in some cases, I had them for you to use. Like this student used beets, and you repeated the experiment with beets, and you figured out the concentration of beets. And we saw that beets, for example, have more sugar in them. They have a 0.4 molar concentration. That's where the line crossed the x-axis, crossed the 0% mass change. And we saw that different fruits and vegetables had different concentrations of glucose or sucrose, of solutes. Okay, so hopefully you remember that lab a little bit. And I'm going to show you an example of a calculation we could have done from that lab using the two equations for water potential and solute potential that are on your formula sheet. So you could have been asked, for example, to find the water potential of a 2 molar sucrose solution. So at 20 degrees Celsius, because that's kind of about the temperature that our room was. So to find this out, the first thing we need to do, and I'm cued to this by the fact that they gave me temperature and molarity. So I'm cued to the fact that I'm going to need to use the solute potential equation, this one, because it has concentration, C, and temperature in it. So I plugged in ionization constant, which is 1 for sucrose, as my formula sheet says. Remember, for salt, NaCl, it's 2. My concentration, which is 0.2 molar, that was given to me. My constant, R, that again is on the formula sheet. And then my temperature, I did the given Celsius plus 273, because that's what my formula sheet told me to do, to get Kelvin. And then I multiplied that all through, and I get negative 4.87 bar. Now that is the solute potential. I need to find water potential. To find water potential, I use the water potential equals solute potential plus pressure potential. And I take my solute potential, and I remember that since this is a beaker, it's an open container, and open containers always have a pressure potential of 0. So I'm really doing negative 4.87 plus 0 equals negative 4.87 bar. So this would be the water potential of this beaker at this temperature with that concentration of solution. So that's it for tonicity and water potential.